So we need to learn how to draw Lewis structures for covalent compounds. There are different approaches to drawing Lewis structures. How you get there doesn't really matter, but we should all end up with the same Lewis structure. Okay, so this is the method that the book presents. The first step is to write the correct skeletal structure, and that means figure out what atoms you have and how they're connected to each other. So this is just going to show relative positions. And this can be a little tricky because there's some more advanced stuff that we're not going to talk about that would enable you to predict how they arrange themselves, but we don't want to go there because we don't need to. So the one thing you should definitely remember is that hydrogen atoms are always terminal, meaning they're at the end, they're on the outside, because hydrogens can only make one bond. They only have one electron to share. Hydrogens only make one bond. So they can't be in the middle of a larger atom where they would be bonded to 2 or 3 or 4 other atoms. So hydrogens are always on the outside. Another thing to kind of help you is that many molecules tend to be symmetrical. So if you're not sure which one goes in the middle, try making it symmetrical. Of course, there are exceptions to that, but just a thing to try if you don't know what else to do. Sometimes on an exam problem in the homework, it'll tell you, make this the central atom. Carbon is the central atom. That's telling you, put carbon in the middle and attach the other stuff to it. The next step is to figure out how many valence electrons do you have. So look at each of the atoms, find them on the periodic table. The group number tells us how many valence electrons, add them up. Okay? If you have an ion, then you need to adjust that. If you have a negative ion, that means you have to add electrons. If you have a positive ion, you need to subtract electrons. The next step is to spread those electrons around. We're trying to give everybody an octet, except for hydrogen. So the first thing you have to do is you have to put 2 electrons between each pair of atoms that are going to be bonded to each other. Because there has to be at least 1 pair of electrons or it's not going to bond. And then put the lone pairs around and try to give everybody an octet. Sometimes that works, sometimes it doesn't. If you don't have enough electrons, then you're going to form double or triple bonds. And you do that by taking lone pairs and moving them into bonding positions. So those are the instructions. Let's do some examples. Let's write the Lewis structure for carbon monoxide. So the first step is to figure out how these are going to be arranged relative to each other. Well, since there's only 2 atoms, it's pretty simple. They're going to have to be next to each other, right? They're going to have to be bonded to each other in some way. So that's the first thing. Next, we find how many valence electrons do I have to work with. So we find carbon on the periodic table. It's got 4 valence electrons. And oxygen has 6. And 4 plus 6 is 10. So I have 10 electrons that I need to show in this structure. So the first thing I want to do is make a bond between them. So draw a line, remembering that a line is 2 electrons. So I've made a bond, and now I'm going to distribute the rest of them. And just go in pairs. So this is 2, 4, 6, 8, 10. I ran out of electrons. See what happens. Count up what everybody has. So this carbon has 2, 4, 6. This oxygen has 2, 4, 6. They are not happy. Yes?
I realize this is kind of ahead, but would it be wrong if you gave the electrons to the less electronegative atom first?
Well, we haven't talked about electronegativity yet.
Okay. And then, so why don't you place the dots singly at first, like it says in the step?
Well, because that's when you're drawing the Lewis structure for an atom. You would put the electrons singly first and then pair them up. In a correct Lewis structure, the final result will have paired electrons. And so we're just going to put them in as pairs. Yeah.
So carbon it started out with 4, but it looks like it's starting out with 5, 7.
Okay, so The thing is, you do not need to consider who brought the electrons. Okay, this is like a potluck. And maybe you brought a bag of potato chips and somebody else brought lasagna. But it all goes out on the table and everybody gets to share. So even though carbon only brought 4 electrons, and it looks like it's got 5 now, and oxygen had 6 and now it only has 5, we're not going to worry about that. We're taking this pool of 10 and forgetting where they came from. So there is an approach where you would consider where they come from, but ultimately this is easier. Did you have a question? So is everybody happy here? No, in fact, nobody's happy. So this isn't good. One of the things I like about Lewis structures is you can make everybody happy. I mean, where else in life can you do that? This is awesome. Okay, so we don't have enough electrons. That means we need to share more. Okay, so we're going to take one of these lone pairs and make it a bonding pair. It doesn't matter which one you take. So I'm going to pick this one just because. So I'm going to erase that. So there's 2 electrons, and I'm going to make it a bonding pair in here. And now I need to check and see how things are going. Well, this carbon has 2, 4, 6, 8. Carbon's happy. Oxygen has 2, 4, 6. Oxygen is not happy. So we can't stop yet. Oxygen doesn't have enough electrons. That means the carbon needs to share some more. Now, I would not want to take this pair of electrons and put it in here. Let's do it, though, even though it's not going to work out well. Okay, so what happens if I do that? Well, this oxygen still has 6, 2, 4, 6, and now this carbon has 2, 4, 6, 8, 10. That carbon has too many. So what do we do? Well, just take one of these pairs and put it over on the oxygen. Again, we're not considering where the electrons came from. We're just moving them around so that everybody gets an octet. Is this how atoms actually bond? No, of course not. But this is a theory that helps us to describe and predict how molecules are, and it's relatively simple. Now this carbon has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. Everybody has an octet, they're happy. If your structure looks messy or ugly, then just copy it over nearby. Any questions? Let's do another one. H2CO. Sometimes the formula that's given kind of suggests how they are connected. So this makes it look like carbon might be in the middle with oxygen on one side and 2 hydrogens on the other side. So let's try that and see if it works. Wrong pen. So there's carbon. We'll put an oxygen over here, and a hydrogen over here, and another hydrogen over here. This hydrogen cannot be on the other side of this because hydrogens can only form one bond. Question?
I thought hydrogen had to be on the terminal end, so wouldn't it be the left and right, or no?
It wouldn't necessarily be left and right for a terminal. It just means on the outside.
Oh.
So think about an airport terminal, right? You've got the main concourse, and then the terminals are sticking off in all directions,
So
right?
the hydrogen should be near the carbon.
Yeah, the way the formula is written suggests that these 2 hydrogens are on the carbon. And if it said that carbon was the central atom, then you would definitely need to put carbon in the middle and try attaching everything else to the carbon.
Is it wrong if hydrogen is on each side?
No, you could draw them differently.
Like switch up one hydrogen and oxygen?
Yeah, let me get my eraser a little bit fatter so it works better. So you could put the oxygen up here and the hydrogen over there. That's entirely fine. And that's not really changing anything. That's just taking it and looking at it from a different direction. So I'm looking at you and you're sitting to the right of her, but from your perspective, she's to the right of you instead of the other way around. That didn't come out well. Never mind. It's like stage left, right, is opposite of what the audience sees. Is perspective. Okay, so we've got a skeleton. count valence electrons. So we have two hydrogens. They each have one valence electron. And we've got carbon. Carbon has 4. Oxygen has 6. So this time we're going to have 12 valence electrons. Again, we start with a single bond. Start with a single bond to connect these. So there's 2, 4, 6 electrons taken up right there. They have to be connected. Then I've got 6 more that I can make as lone pairs. So let's do this. There's 2, 4, 6. So I've got 2, 4, 6, 8, 10, 12. 12 electrons shown, remembering that each line is 2 electrons. So the oxygen's happy. The hydrogens are happy. Hydrogen's always happy with a bond. Is the carbon happy? No. So I need to make a double bond. So let's take one of these lone pairs from oxygen. Oxygen's in a good place. Carbon is not so much. Carbon doesn't have enough. So oxygen says, well, I've got enough. I'll share with you. So let's take one of these lone pairs and make it a bonding pair. Now the carbon has 2, 4, 6, 8. And the oxygen has 2, 4, 6, 8. And everybody's happy. Yay. Any questions? When we have polyatomic ions, nitrate, sulfate, those guys, we're going to follow the same procedure as for drawing the Lewis structure for a neutral molecule, but then we need to pay attention to the charge and add or subtract electrons to get the correct charge. When we finish the Lewis structure, we're going to put brackets around it and write the charge on the outside, unless you're doing a problem in mastering chemistry and they can't handle the brackets. So let's do the Lewis structure for the cyanide ion. Cn minus. Okay, so this is a -1. Well, this is relatively simple because there's just 2 atoms, so obviously they're going to be next to each other in some way. And then we count valence electrons. Carbon has 4 because it's in group 4. How many does nitrogen have? 5. And then that negative charge, do we add 1 or subtract 1? Add 1. Okay, so that gives us 10 electrons. So we start with a bond between the 2. So there's 2. And then we distribute. 4, 6, 8, 10. Ran out of electrons. Nitrogen's happy, carbon not so much. What do? We share more, right? This guy has enough, and this one doesn't have enough. So nitrogen's going to share with carbon. So we take a lone pair, be that one, and we share it with the carbon. Nitrogen still has 8. Carbon now has 2, 4, 6. We're getting closer. Nitrogen needs to share a little more. So let's take this other lone pair and share with the carbon. Nitrogen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Everybody's happy. That's our Lewis structure. Because it's an ion, we want to put brackets around it and indicate the charge on the outside. Because like NO2 minus is nitrite ion, but there is also nitrogen dioxide, which is a neutral molecule. And their Lewis structures cannot be the same. So we do have to indicate the charge. Any questions? Yes?
So would it be wrong if we didn't put more labels on the dots instead?
If you, do you mean if you drew it, let me see, if you drew it like this? I'm saying, would it be okay if you did it like that?
Yeah, or it could just be like one bond.
Well, you can't just do a single bond here, because then you're not going to have octets. So you do have to have a triple bond. And I would prefer that you not just leave it like this. At the very least, if you need to draw the dots, connect them at least to show that those are bonding pairs. Okay? Any other questions? So let's write the Lewis structure for the hypochlorite ion. Again, the first step, put the element symbols near each other. Again, two atoms, you really can't go wrong. They're just going to be next to each other. Chlorine has 7 valence electrons. Oxygen has 6. -1 charge means I have to add an electron. And so that's going to give me 14. So I start with a bond between the two. That's 2. 4. Oh, that's ugly. 4, 6, 8, 10, 12, 14. Oh, we had enough this time. We didn't have to make a double bond. Is everybody happy? Yep. It's an ion, though. So let's put brackets around it and put the charge on the outside. Because otherwise someone looking at that would say, you've got too many dots in there. That's not okay. So that's hypochlorite.
So you said it doesn't do that in master chemistry, so we just write it and leave it?
You have to put the charge, but it doesn't have any brackets.
You just write it afterwards?
Yeah, what it'll have you do is you'll have to give the charge to one of these. Give it to the oxygen.
You just write like O negative, so.
Well, you'll click on it. Try it.
Okay.
Yeah, it's hard to explain. It's not ideal, but apparently it gets the job done. So, of course, any good rule has exceptions. You have a question?
I was gonna say, can we do an example with a polyatomic ion with a cation, or will we not be bonding?
Well, the only one is ammonium. Ammonium's the only polyatomic cation that we talk
Or
about.
no, like if chlorate bonded to potassium or something, how would you show those all being?
So if you had an ionic compound with a cation and an anion, you would just draw the Lewis structures for each of them separately and just put them next to each other.
And then the polyatomic ion would look, for instance, like what we just did, just within its bracket,
Right.
and potassium next to the cation.
Yeah, so if this, was potassium hypochlorite, then potassium would just be sitting over there. So there are exceptions to the octet rule. So to have something that follows the octet rule, you have to have an even number of electrons. There are molecules that have an odd number of electrons. One example is my favorite molecule, No. Okay, nitrogen has 5 electrons, valence electrons, oxygen has 6. That's a total of 11. What do? You cannot make octets for both atoms with 11 electrons. So what you do is you just write the best Lewis structure that you can. So the best thing that we can come up with is to do it like this, which drawing those electrons as shared electrons as lines would give you this. So one is going to have 7 and one's going to have 8. And the way you decide which one has 8, it has to do with electronegativity. But we haven't talked about that yet, have we? See, I have these deja vu moments in class because I've given these same lectures so many times that I forget what I've told you. So that's why I have to ask sometimes. Do you need to be able to draw that structure? No, I just want you to know that it exists. Okay, so there are structures that have an odd number of electrons. They do not satisfy the octet rule, but they can still exist. Another thing that can happen is you can have an atom that is satisfied with fewer than 8 electrons, other than hydrogen. And so here's an example, boron trifluoride and boron trihydride. Boron is one of the smaller elements, right? It's element number 5. And so boron will sometimes be satisfied with 6 electrons instead of 8 because he's a little guy. You don't need to remember that boron does that. but you just need to know that it can happen. Some of the smaller elements can have fewer than 8 electrons in a Lewis structure, and that may still exist as an actual compound. Another exception is when you have more than 8 electrons around an atom. Some of the larger elements can do this. Sulfur and phosphorus can both violate the octet rule. These are called expanded octets because it's bigger than 8. And so we can see that here in this compound, sulfur has 12 electrons instead of 8, and here phosphorus has 10 instead of 8. This can only happen with the larger elements, period 3 and larger. And again, you do not need to be able to write these structures, you just need to know that they do exist. So there are exceptions to Lewis structure, and Lewis theory doesn't explain everything, and yet it's still a very powerful and yet simple way to understand chemical bonding.